Hello, good afternoon, dear ladies and gentlemen. Welcome to our 17th hearing roundtable. This time in our spring roundtable, a very hot topic, robotic cochlear implantation. But before we start, just a short introduction of our hearing group. So the hearing group was founded in the year 2007, and our idea was to be together with all the different people working on cochlear implants, together with researchers, surgeons, audiologists, and all people who work with this topic. This is very important, and this is now our 17th roundtable. We are a group of over 100 people and over 30 departments worldwide working together. Here you see one of our group photos. And at the moment, we are a network of 36 centers on all continents, completely divided all over the world, working together in research science and hearing science. We are coactive and innovative, and also this group works together for robotic cochlear implantation. So we create the standards already since the year 2008, and this is an interactive meeting. So we have CME points, and please raise your hand. You can start questions, and you can do comments. You can do comments during the session. Yeah, please close all your other programs. And now we will start. We have a very, very nice group of people, all experienced in the topic. We have Professor Christian Rack from the University of Würzburg, Professor Marco Caversaccio, who is really the godfather of the robotic cochlear implantation. Without him, this roundtable today probably would not happen. He did most of the basic work. We have Professor Topsakal from Belgium, also very, very experienced since the beginning of the HEARO system. Professor Joachim Müller from the University of Munich. And at the end, myself also engaged somehow together with Marco from the very beginning. And now please enjoy this roundtable about robotic cochlear implantation. And we start with Professor Christian Rack from Würzburg.
Yes, hello everybody. I hope that you can hear and see me. Yes, at first I would like to thank Professor Baumgartner for this nice introduction. And I'm delighted that I can start this great round of talks that we will hear this afternoon. And I was asked if somehow an introductory talk, and today I would like to talk about the importance of resolution for image-guided surgery. When I thought about this topic, I recognized that like image-guided surgery, we have it on two different aspects in cochlear implantation. We have on one hand, this guided electrode insertion. We will hear about this today. And on the other hand, we have this robotic cochlear approach, so the robotic cochlear implantation, and we will hear also great talks about this today. And for both aspects, high resolution imaging is needed. On the one hand, for the robotic cochlear implantation, you need a really good navigation. And on the other hand, for the insertion of the electrode, you need a really detailed cochlear analysis. At the beginning, I would like to talk a little bit about the cochlear analysis and then further on about the navigation. In the field of cochlear analysis, we have learned a lot of in the last year from the great papers from the group from Ontario, Canada, regarding using the synchrotron imaging. They've published many papers regarding this, and I just wanted to show you two here. In one paper, they published like a new frequency map of the cochlear, which is different to the well-known Greenwood map. But also they looked at different structures of the cochlear, and in a recent study, they investigated scala tympani and showed that there are some different tilts of the angles of the various scala tympanis. And this can also explain this high risk of electrode translocation at about 360 degrees. But synchrotron cannot be used in clinic, and also the normal synchrotrons are much too big for clinical analysis, so we have to look for something else. In Würzburg, we have worked a lot in the last years to get a really high clinical resolution. We came down to a resolution about 100 micrometers using the flat panel volume CT, which is a C-arm based technique. And we did many studies regarding this, and we also implemented this new feature of imaging into the Autoplan software. And you can see quite nicely that in the software, this flat panel volume CT, especially with the secondary reconstruction, the cochlear and also the electrode can be visualized much better. And also the cochlear duct length was much more accurate, and also the inter-rater variability. Just recently, we published a study in which we could show that you need at least a resolution of 200 micrometers for correct cochlear analysis, which are not different from micro-CT anymore. But from this, we have developed a formula which can be used in the future. If you have like measurement of the cochlear duct length in lower resolution, you can add your data into this formula and use this to recalculate your cochlear duct length. Also in the last years, the photon counting CT came into the field of imaging. And I would like to shortly just talk about this. Photon counting CT has also quite good resolution, about 200 micrometers. And what's the advantage of photon counting CT? It's a special detector. Normally you have a typical pixel size and energy integrating detector of about 500 by 500 micrometers. And the photon counting CT, it's much smaller with 150 times 176 micrometers. And here, technically, infinitely small pixels can be reached. And it has, in contrast to the energy integrating detector, which are normally used in all CT scans, a really high dose efficiency. We did a study where we looked compared different imaging modalities. We looked at the MSCT, the flat panel volume CT, and the photon counting CT, and could show that the cochlear borders, which you need for cochlear analysis and cochlear duct length measurements, can be visualized much better, and also the electrode detection was much easier. Then we did a second study in which we investigated if it's possible by this photon counting CT to reduce the radiation dose. And it was possible to do a reduction of over 86% down to 3.4 milligray. And that means with this photon counting detector CT, we can scan any patients and all children without harming them. But this photon counting CT has other possibilities. It's really good also to visualize the small structures of the ossicles, or also it's really good, it's really possible with this system to detect also prosthesis. And by this, you can do really nice 3D reconstruction, which could also be the basis for the navigation about which I will talk further on. So if you think about image-guided surgery navigation, I already said there are different factors which affect this. On the one hand, that's the quality of the imaging. On the one hand, there are various techniques developed in navigation. If you think about the technique, there are two different techniques used in medical navigation at the moment. It's an electromagnetic one. It has a higher accuracy, but the problem is of the electromagnetic navigation that it has a disturbance by metal. And you all know that in our surgical field, we cannot leave metal out. So it might be a problem. On the other hand, there's an optical navigation system. They have a little bit lower accuracy, but they have no disturbance by metal structure. But the visibility of the fiducials or instruments can be difficult in optical navigation system. So both systems have advantages and disadvantages. Regarding the resolution of imaging and navigation, I looked somehow in the literature and found already a study from 2003 which have investigated this. I have to admit, since 2003, there were not many, most more studies investigating this, and they showed quite nicely that you want to detect like a difference of here, for example, 0.5 millimeters. There's a really difference in your global accuracy between like here shown 1 millimeter CT and 4 millimeter CT. If you want to like identify structures with greater differences like 2.5 or 3 millimeters, then it does not make any difference so much. But in otology, we need like the detection of small distances, and that's why high resolution imaging is needed. There has been one study from Hanover. They have used this flat panel volume CT2, but this was not a clinical scanner, but an experimental scanner. And they showed that the accuracy of navigation was much better compared to MSCT. And we did also a study where we used this clinical available flat panel volume CT in combination with electromagnetic navigation. We did the fiducial tracing by screws, and then did analysis of different structures, like here's the sinus sigmoideus, the lateral semicircular canals, but much more structures. And we could show that using this flat panel volume CT, and especially a micro flat panel volume CT with a resolution about 200 micrometers, you have a really significant better registration error, but also localization error. So I would like to conclude the first talk. I hope that I've shown you that high resolution imaging is needed on one hand for cochlear analysis, on the other hand for navigation. In cochlear analysis, in the micrometer range, there were structures from the synchrotron. We have a lot for anatomy basis. We could develop a system with about 100 micrometer resolution, and this really helps to do cochlear analysis. The photon counting CT will have its advantages, especially in my opinion, in reducing the radiation and also in the analysis of the microstructure of the middle ear. In navigation, there have been some, but not a lot of studies which have really investigated the effect of low resolution, of higher resolution, and we could also attribute with a study to this. So in the end, I would like to thank you all for your attention, a nice picture from our city, and I'm open for questions now.
Yeah, Professor Rank, thank you very much. I think there are some questions. Now we have some time to discuss. I have actually already a few questions, but I don't want to interfere with my colleagues. So, for example, do you use the Autoplan software prior cochlear implantation or prior any surgery? And if, which version do you use, 5.0 or 4.0? Do you see some advantages or disadvantages? And do you combine at the moment Autoplan with the photon counting CT?
Yes, thank you very much for this question. So first, I have to say we use Autoplan for all our implants at the moment. So we do a pre-surgical planning for all our implants using the Autoplan software, and then an electrode selection by this. The second question was which version we use. We use at the moment the version 4.0. We do not have the version 5.0 yet, but I heard from my colleagues and from our technicians that we will get this in the next, hopefully in the next weeks, and I'm really looking forward because this software should have some advantages. The next question was...
That's okay.
Okay,
so,
great.
So is there anybody from the group who also want to ask? Marco or somebody else? I have more questions, by the way, but I don't want to talk just alone.
Okay, my question is about, you think we can have better results with this photon counting CT for the future, for fitting strategy? What do you think about this?
You know, I believe that we could show that in study that a resolution of about 200 micrometers is needed for a really good cochlear analysis. And a photon counting CT has in its normal resolution a 200 micrometers resolution. So this would help everybody who will use the photon counting CT in the future to do a really good cochlear analysis. But on the other hand, I think we are here somehow at the beginning from a really great story, because we have the possibility now to develop, using these photon counting CTs, our own protocols. We probably will have a protocol pre-op, a special protocol post-op, a special protocol maybe for the Autoplan software, a special protocol for the navigation system. And I think this will make a big, will help to improve all our, the cochlear implantation, but all the navigation, and especially the robotic cochlear implantation.
Okay, thank you.
Yes, so I think, for example, that in good ENT departments doing cochlear implantation, autoplan prior surgery is mandatory. So nowadays, you should not do actually cochlear implantation without autoplan planning beforehand. I think this is really a serious opinion, and it is a fact actually. We're not like 30 years ago, starting with MRIs, starting with CT. We need to know where the round window is. We need to know where the structures are. We need to analyze all these malformations. I think now also with the new autoplan, we also will find a new age of malformation description. For example, we see much more abnormalities, and we can do much more accurate cochlear implantation, especially with this big portfolio of electrodes we have. I mean, we have now electrodes from 34 to 13 millimeters, and we really can attach the electrode to the patient. How is your strategy in Würzburg concerning this topic?
Sorry, there was somebody else.
Yeah,
how is
your strategy in Würzburg concerning all this pre-op workup?
So we, like I said, we do the analysis for all our patients, and then we, like in Würzburg, we are still fans of like long electrodes. So we try to select a long electrode. In what we have learned from autoplan, that the basal, the apical contact should be in an area about 200 Hertz. Then you have a really good cochlear coverage, and this can be reached by the long metal electrodes. Mostly we use the Flex Soft. Yeah. Sometimes we have also experience with the Flex 34, but there are also cochlears where we have the analysis that the Flex 28 is enough to come into this region. And I would like to add another point. If you as a surgeon really do this analysis and know how to use the system, you're getting much better also in analyzing the middle ear structures, the mastoid part of it, because you look much more thoroughly to this structures of the ear and the mastoid, and I think that helps you in cochlear implantation, but also in all your other cases you're operating.
Yes, absolutely, perfectly. And thank you very much for mentioning the 200 Hertz. This is really the issue at all. If you remember, when I started over 30 years ago, the very first patients, and in some countries still today, the patients tell you that they have a Mickey Mouse-like voice. And this is because of the short electrodes, of the mismatch. And this is why we need this insertion down to 200 Hertz to have really coverage of the right pitch at the right point. Yeah, great. So if you agree, I will now continue with Professor Marco Caversaccio.
Right.
Professor Caversaccio is the chairman of the University of Bern in Switzerland. So his predecessor was Professor Rudolf Häusler, also a famous chairman. And Marco is a wonderful person and the inventor, more or less, of the HEARO robot. We shouldn't forget, in the beginning, we had several groups, especially in the US, also continuing this robot, but they all faded out sooner or later because of different problems. And at the end, Marco's idea and his basic work, I will also come to this in my talk later on, led to the situation which we have now. And I'm very, very happy to listen to his talk now. Please, Professor Caversaccio.
Thank you. Okay, ladies and gentlemen, thank you very much for this very nice introduction, Baumi, about robotics, and I will tell you a little bit more about the basic in robotics and the history. As you know, what is important to speak about robotics, at what level we use it. As you can see, we have robot assistance at the moment, but we move again to task autonomy, and this is what we have reached the last years. We have no more, we have not full automation. All the artificial intelligence, big data management is not already included, but I hope so this will also be in the future to include this. This means we are at the level of robot assistance and task autonomy. As you know, several years ago, more than 20 years, was also possible to make the CAD-CAM robot system, this computer-assisted design, to drill out, in fact, a mastoid hole. You can also perform the same what they have performed in Japan to make a drill to be freely moved by the surgeon. This is also possible. As you know, when you want to make a keyhole procedure, we have started, and what you have seen by Chris and Rak, we start every time with planning, and planning is very important. The auto plan system is very important, because otherwise you cannot make a robot surgery. It's the same when you have a Tesla, you must put in where you go, the destination, and so on. We have different steps. We have a planning one time, we have a robotic to the middle ear, we go through the facial recess, then to the inner ear, and last but not least, the robot electrode array must be inserted. This means we can have a whole procedure, or I will show you only a half procedure in this case. As you see, and all was already mentioned by Professor Baumgartner, that Labadie started already 2008 at the Vanderbilt University. There were other groups also in Hannover, Majstani, and Bern, and other group also in the Vanderbilt University, but they have used more a stereotactic frame. They have performed 9 cases at the Vanderbilt University, stereotactic cochlear implantation. They have not moved on. They have also had one problem at that time. This means they have had, because the drill was too, if the speed was too high, they have also have a transitory facial palsy. And often like this, you can stop a project like we can see here at the Vanderbilt University. There are other groups they have used with other robot system. Is the ROSA robot from the group of Zimmer. They have used in Amiens, this is in France. They have used several cases, but they have also stopped the program because they have touched one of the facial nerve. And this is not allowed, because a robot must be better, but not worse than a human. Hannover used or tried to have this robot chick, and they are waiting now to be approved by a notified body. It's also like a stereotactic electrode insertion tool with a linear grill kit, and to use it and to make a cochleostomy. At the moment, we don't speak about electroacoustic stimulation, but about cochleostomy. As you know, we have started in Bern with this HEARO at the time, and the first studies we have performed and published 2019 with several cases. This was calcination and metal together. But Professor Baumgartner will speak more about the HEARO project from Vienna in the next talk. Now, this is one thing to make a complete surgery. But what we can also say, we can make only the last step, like robot electrode array insertion, especially when you want to go for hearing preservation and structure preservation. It could be helpful only to use the last step. It's not necessary to make the whole step altogether. There are other on the market, and you will hear a little bit more by Professor Müller from Munich about the Robotol system. The Robotol system was initiated also by Professor Sterkes and Nguyen in Paris, and they have also published about the restoration of high-frequency auditory perception after robot-assisted or manual cochlear implantation. They have also used this Robotol system to integrate physiology data, not only anatomical data, but to use an intraoperative electrocochleography, especially again for hearing and structure preservation. Another product on the market is Yotamotion from the US. They make this partial procedure. What you need is a normal anatomy in these cases. You have a speed of 0.1 millimeter per second. The cost is about 2,000 euro per operation. They have used also in the group of Bruce Ganz and Hansen, they have used also to integrate the electrography. As you can see here, it's very cumbersome at the moment, but I think this will also be the future to integrate in the autoplan system, not only anatomical data, but as well also physiologic data. This could be helpful also for the surgery, but also for the fitting strategy. The last thing what we have, and this is then Professor Veda Topsakal will speak about for this partial part, is the auto arm auto drive from metal. Is also with a speed of 0.1 millimeter per second. And what we have seen with our tests in Bern, that we have a reduced force variation, means about reduced maximal forces of 18% of a special inner ear model performed in our department by Dr. Ebischer. As general conclusion, I can say, when you want to make a keyhole procedure at the moment, the only with a CE market is the HEARO. When you want to have hearing and structure preservation, normal cochlear anatomy, you can use the system of Robotal, if also CE market. In the US, you have Yota Motion. And we have the auto drive, auto arm, but the auto drive has already the CE market. The questions remain also for the future the same. The precision is very important. This means you must be below 0.5 millimeter when you want to have a keyhole procedure. The risk is clear, don't touch the facial nerve. It's excluded to do this with a robot system. The regulatory hurdles that you have in your countries, economic issue because it could be very expensive, and the clinical usefulness. I thank you for your attention and open for questions.
Professor Caversaccio, thank you very much for the great talk. I'm not sure, I see a question on the screen, but I'm not sure if it's just a sign or if it's really a question. Until we clear that, I think, is it Professor Hagen? I'm not sure. Who want to ask? I can't see that so well. In the meantime, I will ask Marco.
Yes.
Do you think how is the way forward with the robot? I mean, should we all do this? Is it for special departments or for the experts? What do you think?
I think what is the best thing is at the moment to have this in different centers. This is what I think, because as you have seen, there were different projects were stopped. And I think it's you must have good medical engineers in your department. You must have good quality of radiologic data, CT or cone beam CT or photon counting imaging. This means you cannot give this, I can say this weapon in each hand. This means you must have some structure in your department, radiologist, medical engineer. You must know a bit about segmentation. You must know how to work with an autoplan system. This is important. Therefore, I think we go on this line to promote this more and more, but it still needs some time.
Yes, thank you. You're absolutely right. So it needs already a specialized experience department. It's not a robot where you start with your first cochlear implantation. That's not the case.
That's right.
So I have a question from Professor Hagen from Würzburg. Please.
So can you understand me?
Yes, Rudolf, yeah.
Okay, I tried to ask a question already to Kristen Rack because I was interested in MRI instead of CT. This is, in my opinion, for the small children, a very important question. And of course, also the electrophysiological techniques to control the correct position of the electrode intraoperatively. But now we switched to Marco. And Marco, of course, all this research in robotic surgery brought about really very important new technological things and advanced and new things, which are really helpful. But how far are we still from a robotic surgery in routine? What's your opinion?
I think what you see, my personal opinion is like this. We go in the very good direction, but I think at the moment what you can see, you have motor motion, you have Robotal, you have auto-arm, auto-drive. It's easier to make or to make a system only to make the last step to insert, in fact, the electrode array inside the inner. I think because this is without risk, you know, hearing preservation, there are different factors can have an influence on this. But I think on the long term, to integrate the system, and especially we have the drill bit at the moment of 1.8 millimeters, when we can diminish of 1.5 millimeters, we can also diminish, I think, the risk with this system touch the facial nerve or the chorda tympani. I think that in the last years, what we have seen with the different companies on the market, it's easier to concentrate on hearing preservation, but this doesn't mean to stop a keyhole procedure for the future. As you know, sometimes we are working now also based on CT data now performed in 2018. We take this and we do only during the surgery, we do an actual imaging, and we can, to make it easier, but it's clear you perform a CI in 1 hour. We are not there. We need more time, but I think to diminish this in 2.8 centimeters, we need high precision, but we must make attention to not make mistakes automated by the community.
Perfect. Thanks.
Okay, thank you very much. We will have a discussion anyway at all after all the talks together. So I think we will start now the next session. Thank you, Marco. And we'll try the next topic. Yeah, it's my talk. It's about the HEARO system. And the question is, can we believe that a robot is do the surgery autonomous? And I think in the meantime also to answer a little bit the question from Professor Hagen, we are nearly in the routine. So will these robots be capable to do a surgery? And the question maybe is yes, because what we have heard in the independency of any robotic system, the HEARO robot invented by Marco Caversaccio and his team is the completely autonomous surgery. So the surgeon only can start or he can stop, but the surgeon does not interfere at all. And so we will talk now a little bit about the system, and it all started in Bern in Switzerland many, many years ago. Some of you in the audience might remember this suprametal approach from Jona Cronenberg and myself over 20 years ago. And we had a meeting in Bern. And there's not only the people on this picture here, also a young docent, Marco Caversaccio, was there. And actually to look at this simple hole was the start of everything. Because the suprametal approach originally was just a simple tunnel of not even 2 millimeters to go without mastoidectomy, without posterior tympanotomy, directly to the round window or to the cochleostomy. And still a lot of implants are done with this procedure today without the robot. And some 10,000 implants have been implanted successfully. The paper was published a lot of years ago. It took us a few years to publish. And Robert Scheckler wrote actually a preface and he said, I don't think that it's a good procedure, but the authors forced me finally to publish it. And so I'm very happy that it was published. And actually, this was the start of the story. And the talk you will hear now is not my work. It's only partially my work. It was started by Marco Caversaccio and his team in Bern, and also in the Vienna. It's a big teamwork. So you will not deliver a robot to a new cochlear implant department. You need a big team. You need a team of engineers, of technicians. In Vienna, we have the team of MED-EL, we have the team of cascination, and of course, you have a team of residents, assistants who make the pre-op workup. And you see, it's not only me, it's Christoph Arnoldner, Dominik Ries, Alice Auinger, Clemens Honeder, the team from cascination, and of course, the team from MED-EL. And what we can say now, the HEARO is the world's first and only one completely autonomous cochlear implant robot. That means the robot works by its own. What is it? So it's TÜV certified. So our notified body in Europe is TÜV. And what we do is like in a suprametal approach, but it's not a suprametal approach anymore, but we do a 1.8 millimeter tunnel to scale a tympani or to the round window. The point is that you make the preoperative planning with autoplan. So without autoplan, the surgery is not possible. At the moment, we have Autoplan 3.0 and Autoplan 4.0, which is much better. We also wait for the 5.0 version, but Autoplan is mandatory for the HEARO surgery. And what is also mandatory, you need a very good pre-op follow-up. You need pre-op MRI and also high-resolution CT scan. Both images are fused in the Autoplan software. And then with a cup of coffee, you sit wherever you like, in your office, at home, on the beach, and you plan on your laptop or on your iPad. Actually, the Autoplan system is iPad-based. On your iPad, you plan the surgery. So you need to do a trajectory, a straight trajectory from the surface of the head until the scalar tympani. This can be at the end, the round window, but not necessarily. If you might have a better angle or a better access, this can be a cochleostomy. This is dependent on the anatomy. This is very, very important. And then you plan the procedure, you save it on a USB stick, and this USB stick you give later on to the robot. What we can see actually here, the infrared-based robot. It's like in the Steven Spielberg movie. And here you have the arm which does actually the real intervention. So what we do the planning, and then we prepare the patient. The surgeon itself can only start or stop. This is very important. What we do is a skin incision, a regular skin incision. We do then some fiducial screws for the infrared navigation system, and then the robot will fortunately drill. You see here the system. You see an intraoperative cone beam CT. This is in our surgical room. We have a special colleague in our department, is now Dr. Auinger. She is responsible for the cone beam CT scan. So we are not dependent on the radiologists. In Vienna, we do everything by our own within the ENT department. We've here the headrest for the patient, and this is also important. Your patient should not be too big. We had problems in patient more than 100 kilograms or more than 220 pounds. They are too big for the headrest. So the patient don't need to be too big. We have here the robotic arm, which is moving. And here we have the drill. There are two types of drill. There's the general drill for the 1.8 millimeter tunnel. And then there is another drill, which is not for the drilling. We call it milling. So for the cochleostomy to be in the intracochlear part. And here, of course, here we have the system of the control pad. You see here pre-op in the Autoplan system in all the trajectories to see the cochlea, and at the end you make your plan and you change your plan, or you really convince your plan. You can share it with other colleagues, for example. And you see here in blue, you see the drill, and the drill goes, here you see in orange color, the chordae tympani, in yellow color, the facial nerve, the ossicular chain, and you find a nice, straight, direct trajectory safe into the scalar tympani. Of course, you see all the ossicles, incus, malleus, stapes, and it trains additionally your abilities in anatomy. So we have a patient preparation, an adult patient. It's not for pediatric use, and it probably will not be for pediatric use very soon, but in adult, it works very well. A person in between, let's say, 60 kilogram to 100, 105 kilogram. You make the incision, the fiducials. The imaging is very important. We do not rely on foreign images anymore. We need to say that at least in Austria, the standard of the images is not very accurate in all departments. So you need a very accurate pre-op follow-up of CT scan and MRI scan. This is very important. We have done now 6 patients, 6 adults. Tomorrow, on Friday, 12th April, we have our 7th patient here in Vienna. We started with a patient with a 4 millimeter ossification, and this worked very, very well. You see here some slides on that in the basal turn. We also had other patients. We also tried one patient with a complete ossification of the system, which also worked at the end. And what I want to tell you, we have safety margins. So we see on the Autoplan slide, we have a safety margin here on the facial nerve of 0.5 millimeter, which is usual also in a regular standard surgery. Of the tympani, we have about 1.8 millimeter, and the drilling depth, so the drill until the scalar tympani is nearly 31 millimeters. So here we see at the end what we give to the robot, and what we see in the system accuracy after 6 patients, we have an accuracy of 0.02 millimeters. So that means the real outcome from the surgery is 0.02 of a millimeter to the prior planning. No navigation system worldwide can do that. You only can do that with the HEARO. We have also an entrance into the scalar tympani of 0.03 millimeters, 3/100 of a millimeter. And at the end, the positioning of the electrode. So our electrode target is 0.1 millimeter in mean after 6 patients. So far in our adult patients, we use the Flex 28. For the HEARO surgery, you only can use the Flex electrodes. You can use the Professor Müller electrode, the Flex 34. You can use the Flex Soft. You can use the Flex 28, the Flex 26, the Flex 24, and the Flex 20, or a short Flex electrode. And we have now, in all cases, as Professor Rack mentioned, the very important 200 Hertz coverage. And here you see there's the surgeon. The surgeon is doing nothing. Yeah? The surgeon is observing the robot. So you see that the robot, that the robot is doing alone. And you just observe the system. You see here how it works into the skull. You see the drill. The drill is very important. So it's a very special drill who does not hit along with with just some thousand rounds per minute. It's not like a regular system. It's not 60,000, so it's below 10,000 rounds per minute during drilling. And if the system is milling, it's even slower. You see also here the system again, how it works with the HEARO. And also here more in detail, the drill, and also at the same moment, the irrigation and the flushing. Again here. And here you see very important, the permanent facial nerve monitoring. And you see here in blue, the resistance, the drilling resistance from the bone. So here you see a resistance from the bone. That means the drill is still drilling. Here at 28 millimeter, this is our target position. So the drill is, we have here the facial nerve, chorda tympani, permanent Medtronic 3.0, neuromonitoring, and we have 0 Newton resistance. That means we are already in the scalar tympani. At the moment you have any resistance left, you are still drilling. Here you see again the system, how it works, chorda tympani, facial nerve, and here the drill will come, and you see here milling, and here we are at this time. So then you change to the drill for the cochleostomy or for the round window opening. This is another special drill just for this. And you see on the other hand here, my colleague checking on the screen that everything is okay, that we are on top what we wanted to have. And here we see the post-op cone beam CT in the operation room to make sure that everything is all right. So tomorrow is our 7th surgery. Our record so far is 4.5 hours, but you must not forget more than 1.5 hours is only safety measurements. We had no facial nerve problem so far, no chorda tympani problem. This is very important. With an accuracy of down to 100 millimeter, and we had no issue also in the other surgeries in Europe worldwide because of chorda tympani. We've now in the departments of Bern, Brussels, Antwerp, Düsseldorf, Montpellier, Oslo, and of course Vienna, 65, in the meantime 67 surgeries so far, and we had not a single chorda tympani issue. So this is already better than a standard surgeon is now. We shouldn't forget, you will have a chordal tympani sensation in up to 20% of cochlear implantations, even with the very best standard surgeon. We have no issue with the facial nerve, and it works very, very nice. So the HEARO is the only one system at the moment who is fully licensed and who does the cochlear implantation autonomously, but we will listen later on to other talks. We have already the next step of evolution. I personally wanted to call it Super HEARO, but you will hear this then from Professor Topsakal. So I thank you for your attention. And now my question is there any acute question or any remark to the talk about the HEARO?
Baumi, you hear me?
Yes.
First of all, congratulations to your overview of the talk of the HEARO. I have only one question. Do you think in the future, only to make cochleostomy, we can also perform a true keyhole procedure, or you have performed already in these 6 cases, in each case a tympanometal flap?
Yes, super question. Sorry, I forgot to mention. We did the first 3 cases with tympanometal flap for security reasons. We've also nice videos from this. I did then the 4th case, as to my knowledge, the first case without any tympanometal flap at all. So our surgery 4, 5, and 6, and also tomorrow, 7, will be completely without tympanometal flap, just the robot. And we were really very happy about this. And it worked wonderful.
Okay. Thank you. I agree.
Yes, so then let's go to Professor Topsakal from Belgium. I understand the blues. Yes, exactly. So these are very simple screws like you had from Entific or in maxillofacial surgery, self-taping, self-drilling screws. They are set during the surgery. This takes about 5 minutes, and this is true. The blue screws are the references for the infrared navigation. And then you remove it. To remove the screw takes 2 minutes. It's very simple. Okay, at the moment, I do not see any other question. So please, Professor Topsakal, I want to listen to the Super HEARO.
Thank you so much. It's a privilege to be on this panel with all pioneers and people performing HEARO and all robotics surgery. It's a group of very, let's say, highly experienced surgeons. It's a quest, and in this quest, I always find myself defining definitions. So I want to take you back a little bit in the next 5 minutes to semantics and what we do. Semantics, what is a robot? On the left side, you see a device already patented in 1932 by Molinex, and in Dutch, it's called our kitchen robot. It actually cuts in a very standardized way your vegetables. And that's one of the goals. We want to standardize RCI outcomes. But in between, since 2015, people are working on a real kitchen robot. You see 2 robotic arms, you push a button that says spaghetti, and it makes you spaghetti. So what's the difference? Well, what's the difference? We need to be careful on how we define the procedures that we are performing with these highly technological tools. And then you go to the definition of what is a robot. A robot is a machine. It's technology that's providing this machine, but it's programmable. If it's not programmable and if it's steered in a master-slave way by the surgeon, no, it's preferably programmable by a computer and executes a complex series of actions, not only one action. And it does that automatically. The word comes from a play from Karel Čapek's. I invite you all to put into ChatGPT what is then robotics, what is then robot assisted. Very interesting definitions. And I know for sure a robotologist will be a definition in the future, but we will have to see. So you've nicely shown, Professor Baumgartner, thank you for this, the HEARO system. The HEARO system is a whole set of tools aiming for one target. It's the highest precision in keyhole surgery for cochlear implantation. And it did not come overnight. I would like to go to the next slide. It came through the pioneering work also mentioned here, and we cannot mention it often enough, by Professor Caversaccio and his team in Bern, Switzerland, because they were courageous enough to go with a 1.8 cutting drill to the facial recess. And this at that time was some courage, but it was based on science and it was based on calculations with the whole team and setup. When we started in Belgium, I discussed a lot with him, and he always focused on safety, safety, safety. If there is no safety and you have a facial nerve, the whole program will probably not continue. So we picked up on his work with middle ear. We worked with newer, let's say, updated devices as the HEARO system was at that moment, to the inner ear access. And then Autoplan was also booming as a standalone product, where it was designed as the programming software dedicated to HEARO. It's also available on the market now as an otological tool. Insertion angles can become important. I have not accepted a, let's say, not full insertion of cochlear implantation in a conventional way since we do auto planning. Cochlear duct length became important. I came up with canonostomy, anatomy-based fitting. The post-op images is now in discussion and under research. The system got CE marked, as already nicely demonstrated. More than 6 countries are doing now HEARO. And as we continue along, also mentioned before, the navigation is the highest accuracy in healthcare. Imagine if we can share that with our surgical procedures. So what we also were able to launch in Las Palmas, a recent CI Congress 2024, is Auto Drive. It's unfortunately not called Super HEARO by me, but Auto Drive gives you yet another set of tools added to this system, or addable to this system, but also as a standalone available, that standardizes the insertion of speed. If you want, it also is the maximum control of pressure changes in inner ear fluids. So it's a minimalization of trauma to the inner ear. And that's what we want to pursue in actually our quest towards minimal invasive cochlear implant surgery. Here you see the device as a standalone. And first of all, we tried it, of course, in a conventional case where we did a conventional mastoidectomy, posterior tympanotomy. And you see you have both of your hands free. You can manipulate the round window membrane as you do conventionally. If anything I can say about this device, it's its usability. It does not give you any hurdle in your conventional surgery. Of course, you have to steer it. You have to direct in which way the insertion is being performed. And therefore, you have to do it manually with the auto arm aligner. It's not so difficult, but yeah, that's where actually HEARO's works was coming from firstly. So imagine you do this, and then the insertion is child's play, because the insertion with flex electrodes, well, if the tip goes in, everybody doing flex electrodes knows that the rest is a matter of patience. And in here, you see an insertion being performed at a speed of 0.1 millimeter per second. It's all debatable what is the ideal speed, but it's available. The technology is supplying this. So here also, auto-planned features of 5.0, a post-op image showing it already in the right scala. The scala tympani is now colored and outlined specifically for you for your insertion depth. Imagine we combine HEARO with Auto Drive. In the correct word, we would have a CI robot that does it from the whole beginning towards the whole end. And imagine this is also put out and put forward by Professor Caversaccio, that we did not come up with this overnight. We had to study middle ear access. We had to study inner ear access. We had to align perfectly the middle ear and inner ear access just to be able to do the true keyhole procedure, as you mentioned before. And then Auto Drive can do the insertion in the correct alignment. All these steps and hurdles was taken. And one more thing I want to point out, HEARO 4.0 already auto-planned, but 5.0 as well, is giving you the automated segmentation of the individual anatomy, it's giving you a suggestion. This would be the ideal drilling trajectory in the terms that we define it currently. So yes, we are pursuing higher levels of autonomy with HEARO with this. I would dare to say we're going towards level A4 of robotics. Putting that aside, and to sum up, here you see our first case that we did a drilling trajectory with the HEARO, and then we used actually the auto drive to do the insertion in the first case of our series in Belgium. Having said that, I can also confirm this was a full insertion with the autoplant post-op imagings. And I would like to conclude with, let's point out why we are doing this. It's clear that the accuracy and the precision of this device is something we like in otology, and the system provides it at the best in healthcare possibly available today. Repeatability is something that we want to standardize the outcomes. Reliability, you have shown, Professor Baumgartner, an anomaly. We did also a couple of cases with challenging abnormal anatomies, and the system provides all the time that what you program it to do. So it's very reliable. We have some studies now on noise exposure. We say we do no mastodectomy, but we have to prove what's the use of it. So it really has less noise exposure as well. So probably it is paving the way towards, let's say, the maximum minimalization of trauma and electroacoustic stimulation, perhaps in the ear, but for sure, it's going to standardize the CI outcomes. As I said, since we are doing robotics, also in our conventional surgery, we don't accept incomplete insertions anymore as a successful CI surgery. So it's already improving in conventional surgery, the quality and the outcomes for our patients. And as you also said, if this becomes, let's say, standard, the surgeon is pointing towards the future and we don't need to do anything anymore. I would like to thank you for your attention, and I'm open for questions.
Professor Topsakal, thank you very much for this great talk. And it's really outstanding. It's the very first time that I did see both auto-arm, auto-drive procedures live in a surgery, also with the HEARO. So really congratulations. So are there any remarks or questions from our group or from the audience? So then I will ask, is there one? Yeah, Marco, please.
What is the team? You know, we have seen is a paradigm shift in the last years. 20 years ago was one man, one goal. Today is the question, how many people you need for making an operation? What is the standard at the moment in Brussels? Is how many people are involved, because also for the cost, etc. You can tell us a little bit, what is your team, the peers, the control in Brussels now?
Yeah, I immediately have to admit, I have not succeeded doing a HEARO procedure on my own from A to Z. It's not possible. That's a correct and honest answer to your question. I also have to admit that the first case, I think all of the engineers of Cassé Nation were present, but you have to have a brain team or thinking decisive team, and I've always involved and invited engineers into that. I've taken radio protection courses myself, so I am able to use the XCAT on my own. But I have to say it's convenient if somebody else does that, because you're focused on so many things, so you cannot be focusing on the highest level of imaging. So there is a whole team behind it. In terms of, let's say, the nurses, we don't need to forget that everybody needs training when we use this device, but they all accepted it very well. They've been trained, let's say, a week before, and they could perform. And they've been asking questions which were very valid. Can we not, win time if we do this or this? And I have to say, in the beginning, the time was no issue. Our first case was 6.5 hours. Our latest cases are around 2 and 3 hours, maybe. We can do 2 HEAROs in one day. But the paradigm shift, I think that's, insights in gaining knowledge. I have to say, in the beginning, we were quite, let's say, flexible on screenings. If the facial recess was big enough, we say, okay, let's go for HEARO. but we were opening the tympanomeatal flap and there was some room to manipulate the electrode if we did not have a swift line. Today, we are also screening, I have to say, a bit more stringently. There where we screened 10 patients and we could do 8 in the beginning. Now we screen rather 10 patients and we can do 2 or 3 because we take into account the orientation of the round window membrane. And we say, okay, but maybe this case is a bit challenging and so on and so on. So these are, let's say, we are gaining more and more insight on this.
Thank you very much.
I maybe have a question regarding this auto drive.
Of course, I'm listening.
Yeah. So which speed did you use? Did you use always the minimum speed, or is there a possibility to change it? Or does it make sense to have like changed the speed during insertion time?
Yes, this is a very good question. And this is also something we need to research actually all together. We use the lowest speed, which is 0.1 millimeter per second, but you can change it. And you can also, let's say, stop the insertion. And since it's a tunnel, and since it's actually a robotic setup with a head clamp, it will not move and you can decide. So imagine I did a couple of electrocochleographies conventionally, and then suddenly an engineer says, stop, I lose a signal. What do you want to do? You stop, but you cannot hold that position for a long time, and then you have to quickly decide what to do. I also witnessed this, let's say, with auto drive. You have to be careful if you use auto drive in a conventional way that you don't have an anesthesiologist leaning against your operating bed, but it moves, or you do it yourself by accident sometimes, or your resident. So these are very interesting things that we need to work out. What is the correct insertion speed? What can we learn from electrocochleography signals if there is residual hearing in that individual ear, and what are the algorithms that we have to come up with? Thank you so much for this question. And the honesty is, I don't know the answer.
Peter, how much was the additional work to mount the auto arm on the already existing HEARO system?
I have to admit also we did a little cheat because auto drive is CE marked, so we used actually an arm to use the tunnel that HEARO did. So this is something under development, but it was not a big burden to do so. It's actually the same way as you would do it conventionally. So it's not a big burden, but for sure it is something I pursue to develop further on, together with the whole engineering team and minds behind this, let's say, product.
Yeah, great, thank you. So I would suggest we listen now to Joachim Müller, and then at the end we will discuss all together.
Yeah, good afternoon, everybody. Thank you for inviting me to be part of this panel. I also want to thank especially Marco Caversaccio for infecting me a little bit with the robotic virus, and with a slide that Wendy will share for me. I feel a little bit like Baumi, sitting in front of the screen with a coffee. And the screen share comes automatically. So we have gathered some experience with the Robotol system, which was introduced by Olivier Sterkers many years ago. And the idea was driven half being fascinated from technology, but also half influenced by the fact that we should look how we can do better in the future. And we know from Punesh's work and from others that we should preserve the structures and the hearing of the inner ear, and we are better if we do it slowly. And when we consider the slow insertion, as you see in the video on the bottom, the robot can do it much slower than a surgeon would do. Having an electrode insertion over 5 minutes and 43 seconds which is the time for a Flex 31. For a Flex 34, it's even longer. That drives you crazy once you are the surgeon and you want to keep your hands without vibrations and jitter the electrode into the inner ear. So that's the reason why the project from Sarah Traut and Clemens Stiel was started to take care of the robotic insertion. We also wanted to look how another machine can be integrated into a complex operating room logistics. And that's, so to say, in an ongoing study, the first results. So far, with the first 4 surgeons, we implanted 44 adult patients. Male and female are equally distributed. Because we had the ethics votum for the study, we did not include children. However, the robot arm is certified. So we use it in children, but we do not include into the study. And so far, the robotic usage and the time to get the robot assisted for electrode insertion is 15 minutes. And the insertion time, as I said, is 5 minutes. That's even longer than the video, which is still inserting the electrode in the lower part. So far, we haven't seen any misinsertions, any complications, and the learning curve also for the people in OR was quite steep, and we became adapted to the system. As you see, the robotic arm is a clamp-like holder that fits with the metal electrodes nicely and inserts with the latest version the electrode straightforward in the trajectory that has been taken from Autoplan beforehand to the surgery. That's our experience with the Robotol so far, and I'm open for more questions during the discussion.
Professor Müller, thank you very much. Actually, I have a question. We started Würzburg and Vienna, we started in the 90s, and it was published 96 and 97 with the deep insertion. Now, if you use the Robotor instrument and very slow, do you think you can have a deeper, an easier, deeper insertion as you have done the same patient by hand?
Well, surprisingly, the flex soft electrodes can be inserted very easily. And it is in our hands not the case that it moves in directly and slowly. It needs some guidance with an instrument while the Robotol is pushing the electrode inside. So without a guiding tube, the electrode buckles a little bit. But as soon as you guide the electrode with the hook or with a claw, then it slips in nicely. So this works like a ramp. For the Flex 34, all the surgeons have the experience that the insertion with the Robotol is easier than by hand. And this is at least a result of the trajectory that has been taught us by the Autoplan spin-off from the HEARO system, so that we think more about insertion trajectory and planning. And the Robotol insertion tool is like a projection of the electrode and the trajectory in terms of the round window and the opening of the basal turn of the cochlea.
Okay. You know what? I see, Marco, 1 second. Yeah, please, because I think we have some questions. Maybe first Professor Caversaccio, then we make the questions from the audience, and then we discuss. Please, Marco.
Thank you very much. Very nice talk, Joachim. I have only one question. You have, as you know, HEARO is more than for cochleostomy. You have, I think so, you have made the approach about the round window, and you have used different electrodes. at
Yes.
short term, you see better results for hearing preservation when you use the Flex 28, or you see at the moment there is the same results? As you know, we know from hearing preservation, also from Gunesh and you, etc., that we see that this is only one important step, is to make the insertion of the electrode, but you can also see some trends in your 44 cases to preserve the hearing or not?
We haven't measured the hearing outcome so far because the study is designed to be 1 year, and after that we will compare. So far, in the 44 patients, we didn't observe any vertigo symptoms. And we had also to serve selected patients with stiffer electrodes from a competitor that was not so nicely to be inserted like the flex electrodes.
Okay, thank you.
So the insertion itself goes smoothly, and in terms of result, we look at the end for the results. We have no misinsertions, and we have so far no direct postoperative vertigo.
Thank you.
Okay, then let's go to the questions. I start from the oldest one. So question, I would like to know if robotic applications will increase the indication of a cochlear implant and if they will change otology training of young ENT surgeons. What we answer to this? Yes, but I don't know, what's your opinion? It will change. It remembers myself. I'm now 57 years old and started 1990, and we did appendectomy and gallbladder surgery open. And then in 1991, we had the endoscopic approaches. And I think it's very similar now in cochlear implantation. But what is your opinion, colleagues?
Yeah.
Please,
Okay.
Joachim, you're on, yeah?
Yeah, thank you, Baumi. You're looking much younger than 57. Second, I think what we have seen with the group that is taking care of the Robotol study, that they looked more in detail in cochlear implantation and the details of surgery, and this increased knowledge and also manual capabilities. One side effect of the Robotol system to be inserted, like I would expect that for the Autodrive as well, is that you need to have a clear preparation beforehand with the classic rules of middle-ear surgery with a large facial recess and a wide opening to see what the motorized insertion will do. This is maybe different from what the HEARO or the complete robotic system can do. So after Vedat's talk, I'm a little bit hesitating to run a motorized insertion under the topic of robotic insertion. But it's a kind of an assistive device that helps us to increase the quality. But in the end, it's a result of the pioneering work doing a robotic approach.
I will still come back to this question because it's a crucial question I heard very often. We will not become worse ear surgeons because we will use a robot for cochlear implantation. In contrary, we'll be better ones. If you look in ophthalmology for lens surgery, LASIK, for example, no human being, no ophthalmologist can sharpen the lens in nanometers. And also no human being can go intracochlear in beyond 100ths of a millimeter. We want to preserve that. So I think the robot will improve our skills and we will still have enough work for standard surgery, for cholesteatoma, for any other middle inner ear disease, that we do not forget our skills, which we really need. So I will go to the next question. Can I ask Professor Rack if he has a photon counting CT in his OR? Please, Kristen.
Yeah, it's a pity that I don't have one. Yeah, at the moment, the photon counting CT is only available like at a normal CT scanner, and it's not really applicable, in my opinion, like in a ENT or R, where you do not have really the possibility of the gantry. Maybe in neurosurgical operation or CHI, you can have the possibility. But the advantage of the photon counting CT, it's mainly the detector. So I'm sure that in the next years, this detector technology will also be implemented in other systems like CM-based systems. And then we will have the possibility to use it in the OR as well.
Okay, next question. What happens if during the insertion appears some resistance? Does the robot detect it and stop? So for our HEARO in surgery, we did the insertion by hand, but we had no resistance. So what do you think, Vedat or Joachim? Did it ever happen to you that you had resistance during insertion?
Yeah, it happened. And depending on the speed with the Robotol, and I think it counts in the same for the auto drive, is that the electrode starts to slowly buckle, and then you see that there is a resistance. You can try to correct the trajectory, but by visual observation, you detect that there's a resistance inside.
Okay. Next question. Is there a mobile unit like the cone beam Baumi has in his theater? Yes, it is a mobile cone beam CT. I don't have the exact brand and number. I don't have it now in my mind, but it's a commercial available system. So we just bought it. It is a mobile cone beam CT, yes.
Yes.
So, yeah.
I don't know to say it's from Xoran Technology from the US.
Thank you, Marco. Great. The next question. What about? It's not a real question. Did tip fold over happen? Let's call it like this. Does any tip fold over happen so far? So I answered this straight away. I analyzed I need to tell this public. I had just recently in Vail in the Academy, American Academy Winter Meeting a talk, and we analyzed 3,000 insertions from Vienna in the last 30 years, 3,000 insertions in 30 years. And we had in Vienna not a single tip fold over ever in 30 years in 3,000 surgeries. My US colleagues did not believe that. They said, this is completely impossible. But in our department, it is a fact. So we mainly use Medel electrode. Everybody knows this, that Vienna is very close to Medel, and we never had this problem at all. But maybe what's the other colleagues?
With the robot, we have not had a tip fold over. No, I've not seen. With the robot.
No tip fold over, neither with the robot nor with the FlexSoft, Flex 28 and Flex 34 insertions so far. And there's a paper by Högerle. She did a survey in a 2-center study together with Robert Nünsky in Rostock. And this confirmed in a large patient group that we had no tip folder. There are 2 single cases of tip fold over published in the literature, but I'm not sure how the surgeon could manage with that. And
yes. So my personal opinion is even more strict. If you have a technical tool licensed from a notified body who has such a danger of tip fold over up to 10% published, then you should withdraw it from the market. Because to have complications like this, which ends up in a revision of a patient up to 10%, is not state of the art in the times we live now. But let's go to the next question. Long question. Yeah, is there revision replacement ever happened in robotic cochlear implantation? So in the cases I know from the HEARO series, so of 66, 67 cases, we sometimes change to a manual procedure, but to my knowledge, there was no revision. But Marco or somebody else, I think Marco is the most experienced.
We have no had a revision. But Rob Labadie has published one revision case, and this is very interesting because they have had a kinking when you come out as a keyhole procedure, and then you have an angle of 90 degrees. What can happen here that you can destroy some of these packs inside the electrode, and he has had a revision. Therefore, when you want to make a bed more smoothly, we must make not 90 degrees, but perhaps 40 degrees, that you have no kinking when you come outside from the tunnel. This is important. This was already published one time, and I completely agree with the group of Nashville.
Great, thank you. There's now one question. I want to have this now as last question before we discuss in between us. Is it possible to use MRI to do the image-guided surgery and X-ray after surgery for anatomy-based fitting? Yes, if you have really an intraoperative MRI, if you're such a wonderful department who can afford it, it is possible. But to my knowledge, none of us has an intraoperative MRI available. So, but if there is some sponsor watching this broadcast, please come to us to sponsor one.
Maybe I add there something though. Regarding cochlear duct length measurements in MRI, you have to be a little bit careful because it's still you underestimate the cochlear duct lengths. Especially the apex cannot be visualized in the MRI at the moment. So, but we've done some studies. It's quite normal. It depends on really on the resolution. You have about 600 micrometers normal MRI resolution in the T2 space imaging, and that's normal, like normal MSCT. So it's somehow comparable, but still underestimates. And post-operatively, there is one study which have investigated like half a year later on the electrode contacts inside the cochlea by MRI. That's somehow possible, but I'm not sure if you can use this really to detect your electrodes.
Okay, thank you. So now I will close this part and we will discuss in between the panel. So for example, before that,
Rudolf Hagen has a question.
Okay, Professor Hagen, last question.
This is not a question, but being the actual chairman of the hearing, I have to tell all the participants and the speakers, this was a very fascinating roundtable, especially to hear all the details about this new technology. But in general, let's think about, I see there's an increasing gap between the new technological possibilities and our main task to promote CI worldwide. So we may not forget that this is the main goal for hearing, to bring about CI in general. Nevertheless, it was really a very, very good and very convincing session today. Thanks.
Professor Hagen, Rudolf, thank you very much. We don't give up. Now next. So in this roundtable, we have a pure robotic thing. That's the HEARO, the auto arm and the auto drive. They do more or less automated surgery without a surgeon. In contrary to systems like the Robodoll or the IOTA from Bruce Gantz in Iowa, which are actually surgeons' assistance tools. So they help the surgeon for a better insertion, but they are not autonomously robotic. So I think this is really what we need to point clearly out. And now let's start. I have a question though. I did a lot of cases, some of you know, with interoperative electrocochleography. So we try to go in to measure the electric brainstem responses. And if I understood correctly, I think Marco or Vedat, you now combine this already with the HEARO. Is this true? And if yes, what is your experience?
I can only say in the literature, you find that this integration in the Robotol. There is some group also from Poland and also from France. And there is also from Professor Hansen and Bruce Gantz from Iowa. They try to integrate with iota motion also the electrophysiologic part. This is what I know. We have not, with the auto drive, we have not already started. We use, like you, all the electrocochleography, also the Windows in Windows presentation during the surgery. But I think this will also be included in the auto plan in the near future. This is what I wish.
Vedat, what do you think?
I second those thoughts, and I have to also admit that we have just gotten ethical approvals from randomized controlled studies to do this, also with AutoDrive, also AutoDrive combined with HEARO to see if there's a difference. And I also second the opinion of Professor Müller. When I did echo meetings manually in conventional surgery, it's humanly impossible to do a 6 or 5 minute insertion. And
Right.
And I noticed myself saying, if this is the future of CI, I go ahead and next surgery maybe, because you cannot stop and look at the technical engineer and evaluate the EKG. This should be automized, and AutoDrive can stop and hold that position. And then you can, yeah, as I said, come up with algorithms, what we should do to prevent residual damage to residual hearing.
Yes, great. So this is what we want. If we look to our patients today in 2024, they are completely different to patients from 1990, 1991. We have a large number of residual hearing patients, and with the new system, with the new drugs coming up, don't just tell about the otofalin, what happened in the gene therapy. We have at the moment nearly 100 companies worldwide searching on those inner ear drugs. So there will something come up very soon, and we need to be prepared for that, especially in cochlear implantation. What do you think with the link to artificial intelligence in robotic systems? You think there is a need for that, or are we good enough? What's your opinion?
Are you asking me?
Yeah, but whoever. Yeah, I've now, first was Marco, then Kristen, then Vedat. So Marco, please.
Thank you, Baumi. I think what we need is more data. This means we must make a little bit more with the big data management to include all what you have performed, what you have, the problems what you have in Vienna, what you have in Antwerp, etc. This means perhaps there are some algorithms to correct something like this. And for me, this is artificial intelligence, but we are not there to have deep learning. This is not the case. But I think more cases we have, more we can look about some algorithms to integrate and to make better robot system.
Okay, thank you. Kristen, please.
I think artificial intelligence is really needed for all the field of cochlear implantation, because I think we have still a problem somehow of prediction of our results. You know, we know that we can insert the electrode quite nicely, we can fit the patient good, but it's still, we have a huge variability in the outcome. And maybe using all our data, like Marco has said, also together, this could be a possibility to enhance this, and then also add all this new also knowledge what we have got from surgery, especially from the robotic system. Maybe sometime we will have also measurements of the resistance, of the impedance during surgery, all this kind of information together. That probably will help us to be better, but on the other hand, to predict better our outcome.
Thank you. Great talk. Vedat, what do you believe? Artificial intelligence.
I am a strong believer of input determines output. I don't need artificial intelligence to decide if I want to have a glass of wine with my dinner. But I second all the things that have been said. If we have the big data, it's a very strong computing tool to determine and maybe predict determinants of how to preserve residual hearing. But for the moment, I think there's a whole field open for, let's say, how to deal with processor strategies and signal stimulations and so on. So I expect the first benefits of artificial intelligence on the part of the processors, how they're being programmed, because these data, there's 1 million people already wearing a cochlear implant. We just need to pull it and drive it into these calculating systems. That's what I believe. And there's only, as you said, 67 or about 70 HEARO patients worldwide. So we need to define this.
Okay, thank you. Before we close, there was a final question. I want to answer this. How important are flexible electrodes for robotics? They are vital. They are vital. Without long, soft, and flexible electrodes, robotic surgery is simply impossible. So this is really the basic of robotic cochlear implantation. And now, yeah, thank you very much for listening to us live or later on YouTube. Thank you so much. This was our 17th hearing roundtable, and our next, the 18th, will be on 13th of June this year, in 2 months, 13th of June, Thursday, 3 p.m. European summertime, and it will be bilateral cochlear implantation. So thank you very much, and thank you very much for listening, and best greetings from Vienna.